Have you ever looked up from the bottom of a swimming pool and noticed how the water's surface sometimes looks like a shining mirror? That's not magic, that's physics. Normally, when light travels from a denser medium, like water or glass, into a rarer medium, like air, it bends away from the normal. This bending follows Snell's law, N1 sin I equals N2 sin R. But something fascinating happens when the angle of incidence becomes larger than a special value called the critical angle. Instead of refracting out, the light reflects completely inside the denser medium. This remarkable phenomenon is called total internal reflection or TIR. Mathematically, the critical angle is given by sin C equals N2 divided by N1, wherein 1 is greater than N2. As you can see in the diagram, when the incidence is less than C, light refracts out. At exactly C, it grazes along the boundary. And beyond C, the light reflects back inside like a perfect mirror. Now, let's use this phenomenon inside a prism. A prism is simply a transparent optical block that bends or redirects light. In a right-angled isosceles prism, with angles 45, 45, and 90 degrees, something amazing happens. When a light ray enters, it strikes the face at 45 degrees. This is greater than the critical angle for glass air, which is about 42 degrees. So instead of escaping, the ray undergoes total internal reflection. Such prisms are called total reflecting prisms because they never allow light to escape and they reflect it all inside. That's why they are widely used in periscopes, binoculars, and cameras. The simple law behind it, if angle of incidence is greater than the critical angle, refraction does not occur. Only reflection takes place inside the medium. Look at the prism diagram. Notice how the ray reflects inside instead of leaking out. Here's the first application. Take a prism with angles 45, 45, and 90 degrees. A light ray enters normally at face up, so it goes straight in with no deviation. At face AC, it strikes at an incidence angle of 45 degrees. Since this is larger than the critical angle of 42, the ray undergoes TIR. Now, the ray reflects and emerges from face BC at a 90-degree deviation compared to its original path. And here's the beauty, this deviation happens without absorption or intensity loss, unlike ordinary mirrors. That's why prisms are preferred in optical instruments such as periscopes, where you need to bend light exactly 90 degrees. Look at the ray diagram. The light comes in, reflects, and exits perfectly turned. But prisms can do more. If a ray of light enters normally on the hypotenuse AC, it passes undeviated inside. Then it strikes face about 45 degrees. Since 45 is greater than the critical angle, TIR occurs. The ray reflects again at face BC. After two total internal reflections, the ray emerges parallel to its original direction, but exactly opposite. In other words, the deviation is 180 degrees. Mathematically, total deviation equals to times 90 degrees, that is 180 degrees. This property is used in binoculars, where prisms flip the image without losing brightness. Look at the diagram. Notice how the beam comes back exactly opposite its starting direction. Prisms can also correct an image to make it upright. When a light ray enters parallel to the base of an erecting prism, it undergoes two total internal reflections before emerging. Because of this clever geometry, the final image is upright or erect, though slightly shifted sideways. This is called an erecting prism. They are used in slide projectors and field binoculars where it's important to see an image the right way up instead of inverted. In the diagram, notice how the emergent ray stays parallel and the image PQ remains upright. Let's solve a numerical example together. Question: a ray of light is incident normally on one face of a 45, 90, 45 prisma. If the refractive index of glass is 1.5, what is the angle of deviation? Step 1. At face AB, the ray enters normally. That means no deviation. Step 2. At face AC, the angle of incidence equals 45 degrees. Step 3. The critical angle is sine inverse of 1 divided by 1.5. That equals 41.8 degrees. Since 45 is greater than 41.8, TIR occurs. Step 4. The ray reflects, travels to face BC and emerges normally. So the total deviation is 90 degrees. Final answer: the prism deviates the ray by exactly 90 degrees. Check the diagram, it matches perfectly with our calculation. Let's quickly wrap this up. Total internal reflection happens when the angle of incidence exceeds the critical angle and the light reflects fully inside the medium. A total reflecting prism can bend light by 90 degrees, flip it by 180 degrees, or even produce an erect image. Remember, the critical angle depends on the refractive index. Sin C equals 1 over mu, where mu is the refractive index of glass. This principle is the backbone of optical devices, periscopes, binoculars, projectors, where prisms are far more efficient than ordinary mirrors. Why? Because they reflect with almost zero loss of brightness. So the next time you peer through binoculars or enjoy a projector show, remember, it's not magic, it's total internal reflection at work. I hope this session gave you a clear picture of how prisms harness light. See you in the next class with another fascinating concept from physics.